Well, I'd like to start, as have all the other speakers, by thanking Irfan and the other organizers for putting together this wonderful program, and also to congratulate Irfan, John, and the rest of the collaborators on their new center. It's very impressive. I'm going to talk about, actually mostly, some recollections from my time in Berkeley. I was a grad student of John's, and I've modified the date of my talk so that I can legally wish John a happy birthday, as well as thanking him for basically setting me on my career path and teaching me, I think, most of the physics that I know today. So thank you, John. So I was in the Clark group from about 1984 to 1991. And one thing that I think everybody from that era knows is that it was an extremely dynamic group. There were a lot of people in the group itself, but there were also a lot of visitors and kind of people that worked with other people in the group because it was such a productive place to be. So I tried to write down the names of all the people that I interacted with during my time there. And this includes people that left soon after I joined the group. For instance, John Martinez left just a few months after I joined, and some people that started a few months before I left the group, such as Andy Miklich. And all the people that are underlined here are present here in the room. Now, this is quite a number of people. There were also quite a number of projects that were being pursued, and I've tried to list all of the projects that I was sort of aware of while I was in the group, and I've written and read all the ones that have to do with noise. And anybody that's worked in John's group knows that noise is the signal for many people in the group. Now, this is a really impressive number of different topics, and I have no idea how John managed such complexity. But he didn't spend all of his time working. He would also organize fun events for the group. And this is one that I happen to have some pictures of. This is, of course, before pictures were easily done on a phone. This was a ski trip in Bear Valley. It was either 1989 or 1990, I'm not sure. And as in any group picture, you can always pick John out immediately. He's the tallest person in the picture. Now, he's challenged slightly here by Martin Hurleman, who's almost the same height as John, but not quite. And also in this picture, you can find Greta and Elizabeth. I have some other pictures. Here's a picture of John looking back, I think at me. I think I took this picture. And then some other people that were in the group at the time, Ruth Ellen Thompson and Nancy Missert, as well as John Schmidt, as well as my wife Ning, who I married near the end of my time there and was here yesterday. And then there's no picture of Fred in this picture, but I did find a picture from when Fred took us hiking, I believe on Mount Tam. And he was a big member of the group. He contributed a lot to my research, and I want to thank him as well. John was famous for having parties at his house. It was a tradition that he would always have a Thanksgiving dinner every year, and this is not actually a picture from his house. I stole it off the web, but these were fantastic events, and they were always, of course, dominated by John's collection of wine. And one thing that anybody that's been to John's house knows is that John will pick out a bottle of wine, and not only will he know what kind of wine it was, where it was made, he'll know where he bought it, and most importantly, how much he paid for it. And he usually paid some stunningly small amount of money for something that was just, extraordinary. That was always a remarkable thing. Now, one thing about John is that I think other people have mentioned is that you always had to get the physics right. You had to do it when you spoke with him, you had to do it when you gave a talk, and most particularly, you had to do it when you wrote a paper. And this was where you really found out that you didn't understand anything, and it took many, many iterations. I think other people like Christian and Fred have alluded to this. And basically you would hand John your draft, and he would give it back to you a few days later, completely scribbled over. You'd give him another version, he would give it back to you, and it would take, 6, 10, 12 iterations to get a paper through his editorial comments. But the result was always an excellent paper. The physics was right, the description was simple, it was clear, there was no clutter. And there were 3 papers only one of which I was an author on, that came out during my time there. And these have been shown by Michelle and other people. These were, in my opinion, the papers that impacted my future career the most. And they were basically the first qubit papers that came out, I think. In particular, this paper right here that John Martinez was first author on, showing energy level quantization in a phase qubit, or sorry, a Josephson junction. My own contributions were taking these Josephson junctions and trying to measure the effect of dissipation on macroscopic quantum tunneling. There were theories for this from Leggett and others. And what I did was I took a junction of the type that Michelle and John Martinez had worked on, basically a niobium lead-indium junction. Tunnel junction is right here. And I put a metal thin film resistor across it in order to provide dissipation. And the measurements showed that the rate of macroscopic quantum tunneling, is represented in this plot, fell by about a factor of 300 due to this dissipation, in very good agreement with theory. And also the rate of thermally activated macroscopic quantum tunneling agreed with theory as well. Now, I would like to point out that this experiment would not have worked if Fred had not already figured out the hot electron effect that he described when he was talking about his work on squids. And very importantly, this little thin film resistor has a big metal flag on it in order to cool the electrons that would get hot every time the junction switched. And this really made this experiment work, and that was thanks to Fred. Finally, I graduated in 1991. This was a picture of all the people that graduated that year. Mark Ferrari, who's actually still in the Bay Area, Non Chung Fan. My wife graduated that year, and Ruth Ellen. And then I have a picture of John putting a hood on me, and it's not threatening. Now, two members of John's group that actually left before I joined, but played a big part in my life, were Michelle and Danielle. And these are both pictures taken at John's house. I don't know if this was a Thanksgiving dinner or some sort of farewell dinner, but these two individuals, along with a third one, Christian, founded the Saclay Quantronics group, which I will take the liberty of calling it the second campus of John's group in Paris. And this was a really excellent group. And there is one other person in this picture right here who was one of the earlier members of the Quantronics group as a student. This is Hugues Potier. And this group has now grown significantly and is really a force in its own right, as we know from the talks that have come from that group today. Now, in 1997, I joined the faculty at UC Santa Barbara, and I worked there for 7 years. And then I had the good luck to be able to recruit John Martinez, who is at NIST Boulder, to the UCSB campus in 2004. And we joked many times about the fact that we were somehow fated to work forever on our thesis project. John, actually with Christian, had at that point taken the Josephson junction and turned it into the phase qubit. And he brought that technology to Santa Barbara. And I collaborated with him on many of the advancements that we pushed forward for the next basically 11, 12 years. And so we took, in terms of technology, this device that I used for my MQT experiments and pushed it forward. This was an experiment with 4 qubits and 5 microwave resonators that Eric Lucero, I don't know if Eric is still in the room, demonstrated a heavily compiled version of Shor's algorithm with. This is a 5-qubit linear circuit that Rami Behrens built in 2014. And then this is a 10-qubit circuit that Julian Kelly built just before John's group joined Google. And in terms of experiments, of course, there was this fantastic result from John Clark's group showing the energy level quantization in a Josephson junction. This was really, in my mind, the first demonstration of a qubit. And this has, of course, now been I would say, built upon by many, many experiments, and I just picked one. This was using that 5-qubit circuit to software program, for instance, a 2-qubit Bell state all the way up to a 5-qubit GHZ state, where the fidelity of the state generation here was completely dominated by spam errors. These were randomized benchmarked experiments where the randomized benchmarking error was in the 99.99 fidelity range. So these were completely limited by spam errors. And another experiment that we were able to do, working with John, was to take the phase qubit and couple it to a microwave frequency mechanical resonator, get this device to work, show that we could measure, that we could actually get this mechanical degree of freedom into the quantum ground state at millikelvin temperatures, and drive the system with the qubit and show that we could actually get qubit mechanical resonator Rabi oscillations and generate qubit mechanical system entanglement. Admittedly, with very short lifetimes, but this was kind of a very nice experiment to get done. Now, in October of 2015, I moved to the University of Chicago. I joined the Institute for Molecular Engineering. We're housed in this new building on the University of Chicago campus, which is in Southside Chicago. And this is basically a nascent engineering program. We've picked a number of different areas to hire faculty in and to focus the efforts of this institute on, and quantum information is one of those areas. It's a degree-granting institute. We award undergraduate as well as graduate degrees, and we have our own graduate admissions. And part of this new building, in addition to my labs, David Aushalom's labs, and other experimentalists, we have a brand new clean room, 1 floor below ground. This is a 10,000 square foot user facility, and we're using this now to pursue experiments using superconducting qubits, as well as mechanical devices and spin-based devices. What my group is now kind of focusing on is, I guess I'll call it qubit interconnects. I think we know at a fairly good level how to locally couple qubits together, but the question is, can one couple qubits remotely to one another or to other systems, such as, for instance, spins? And so we're exploring ways to do this using both mechanics and optomechanical systems. So we're building structures like this to try to, for instance, generate Lamb waves that can interact with spins, or optomechanical systems like this where we can hopefully frequency convert coherently between microwaves and optics. So I want to say what the motivation for that last sort of area of research is. What we'd really like to do is to try to build a system that can do quantum communication. And so the idea here is that you have Lucy who wants to quantum communicate with Ricardo, or at least she wants a completely secure form of communication. They'd like to use classical encryption such as RSA, but unfortunately Ethel has built a quantum computer and makes that not very reliable, so they decide to do quantum communication. And the question is, well, what kind are they going to use? So a very simple one is to share an entangled state of 2 photons, where Lucy gets one of the photons in this entangled pair. And what she does with this is she measures it in one of 3 randomly chosen bases. Ricardo gets the other photon, and he also does measurements using 3 randomly chosen bases. And they then, when they measure in the same basis, when they happen to measure in the same basis, then the data that they get out will be correlated. While if they measure in different bases, the results will be almost, but not quite, random. And so then what they do is, using a classical open communication channel, they share which bases they used for these measurements and pick out the ones where they happen to pick the same one, so that when those bases coincide, they've basically shared information, and that information is still secret, even though the basis is not. But when their bases differ, they can actually do a Bell violation calculation on the results and detect whether there is an eavesdropper there or not. So those results can reveal the presence of an eavesdropper. And this particular protocol is known as the E91 after Arthur Eckert, who came up with it. Now the problem is that that only allows two people to communicate when they're fairly close together, because you're limited by the decoherence rate of these entangled photons in, for instance, an optical fiber, or when communicating through free space by decoherence in free space. So what you'd really like to do is to build something called a quantum repeater, and this is where you need qubits. So I'm just going to very quickly describe how a quantum repeater works. So here's node A. This might be Lucy. Here is node C. This might be Ricardo, and they're going to communicate through an intermediate node, and that they will put these nodes as far apart as they can. But you'll see that with this 3-node network, you can double the distance over which you can communicate, and you can of course extend this indefinitely. So each node has 2 kinds of qubits, a data qubit and a memory qubit, and they each have their own purpose. So in step 1, you entangle node A and node B by sharing an entangled photon pair. You then swap this data qubit into the memory qubit, so now the 2 memory qubits are entangled. You now share another entangled photon pair between nodes B and C, entangling their data qubits. And now what you do is you do a Bell measurement on the photons in the data qubit of node B and the memory qubit of node B. And what that does is it transfers the entanglement to between node A and node C. And then you can perform a swap on node C in order to leave the 2 memory qubits entangled. So that's how you skip one node, and of course you can just do this indefinitely. So this is, in principle, a scalable way to communicate over large distances. So what we're trying to do is to find a way to do this with microwave frequency qubits. Of course, superconducting qubits are what I know how to do, but there's no reason that you should be limited to superconducting qubits. But basically what you need is a way to build a node that is coupled to light. And that's what we're trying to do, and really the focus is on what is this double arrow? What do you put there? That's the challenge. So what we're trying to do is we're trying to build a microwave to optical frequency converter that can serve as that double arrow. We're basing our development on these 1D optomechanical systems that were primarily developed by Oscar Painter's group at Caltech. And they consist of a mechanically suspended nanoscale beam of dielectric material with a series of holes drilled in it. And in this case, we have an optical waveguide evanescently coupled so that we can probe the trapped optical mode in this chirped structure right here. So the idea is that this chirping in the holes creates a localized optical mode, and this can be at whatever wavelength you want, and we're designing it in a standard telecom wavelength. And you also, using the same set of holes, can trap a mechanical mode that's co-located with the optical mode. Now, the frequency conversion comes about because if you pump light into this mode, you will generate radiation pressure that can drive the mechanical mode. And if you drive the mechanical mode, you can modulate the optical response of the material and thus modulate the optics. So that's where the frequency conversion comes from. Now, what we're doing that's different from what the Painter group has done is we are making these structures using piezoelectric materials so that we can take the gigahertz frequency mechanical signal and convert it to a gigahertz frequency electrical signal that we could then couple to a microwave qubit, such as a superconducting qubit or possibly a quantum dot qubit. The way you would encode the information in the optical signal is fairly simple. The idea is that you illuminate the structure with a strong laser signal. That's not where the quantum information is. Instead, you encode the quantum information in the gigahertz modulated sidebands that you're generating with this optomechanical device. And you might, for instance, encode the quantum state that you want to transmit by making the 0 state the one where the 2 sidebands have the same phase, but the one state is where the two sidebands have opposite phase. There's also other schemes that you can come up with. So we've started building these devices, and just very quickly, this is the first generation device that we built. This is all fabricated from aluminum nitride, which is a strong, thin film, piezoelectric material. Our one-dimensional optomechanical crystal is right here, and this is an evanescently coupled waveguide with grating couplers at either end so that we can couple light into and out of the structure and measure what's going on optically. We also have metal electrodes here that allow us to drive the mechanics with an electrical signal all the way from DC to the gigahertz band. And we tested this device by basically measuring the optical response while we drove it electrically. And we could see strong responses at all the mechanical resonances in this mechanically suspended structure, where the lowest frequencies were in the tens of megahertz range, and the highest frequencies were the breathing modes that we were interested in the gigahertz band. And this plot right here just shows that we can coherently take microwave pulses and homodyne detect the response in the optical sidebands and resolve the signals down to driving forces that correspond to a signal as small as 1 phonon in the breathing mode. So this basically shows that we can take a classical coherent microwave signal and encode a sideband on the optical signal. In our second generation device, which is shown here, it again has a one-dimensional optomechanical crystal, but now we're using interdigitated electrodes in order to couple much more strongly to a gigahertz frequency Lamb wave in this completely mechanically suspended structure. And again, using classical signals, we've shown that we can take a modulated electrical signal and drive the optics, but also take a modulated optical signal and get a detectable electrical signal. Detectable meaning weak. We're not in the quantum limit. These are all room temperature characterization measurements, and we're not there yet. But we can at least show proof of principle for bilateral transduction. And this just shows that we can do the coherent homodyne detection going from optics to microwaves now, instead of just from microwaves to optics. So, of course, what we'd like to do is to build quantum repeaters that will allow us to do quantum communication, but we have a long ways to go before we get there. This is just sort of a benchmark experiment so far. So this is my group at UChicago, and here is that image rendered into a 100 nanometer thick aluminum film using a chlorine etcher, just showing we can do stuff in our clean room. And again, I'd like to finish by again thanking John for all of his contributions to the field, as well as to my career and my education. And also this was a picture that was taken in Paris at an event a couple years ago. And this is Danielle Esteve, who unfortunately can't be here, but is here in spirit, I think, if not in body. Thank you.
Andrew, this was a very beautiful talk, but I want to make a comment that sounds a bit childish, perhaps. You were mentioning that the MQT experiment was the first qubit. And my feeling is that to have a qubit, you need coherent transitions. Yeah. So in that sense, I think Yasu Nakamura's experiment was the first one.
Yeah, that's a very fair comment. I think you could argue that the measurement of energy levels shows some degree of coherence, but you're right.
It's promising.
You're right.
It's almost there, but it's...
But of course, Nakamura's experiment was done 6 years later, so...
I know.
Yeah.
No.
But you're right. You're absolutely right.
This was an extremely important experiment that was done here, and I'm not taking anything away from that. Okay, sorry.
No, I agree.
Other questions? So one thing that I found particularly really exciting, actually, I think it's a beautiful talk, Andrew, about the possibility of having this sort of microwave to optical transducing is maybe the possibility of thinking about sort of state transfer from microwave states towards like optical modes, with the idea that at some point you can take all of the tremendous progress that's done in the microwave states and really just make arbitrary, non-classical states of light. And I was wondering whether you could comment on, is that near-term progress kind of robustly building that type of a situation possible? What are the challenges that would get one towards that?
Yeah, that's a good question. I mean, what we're doing is not really manipulating light itself, we're manipulating the sidebands. And so I don't think you can directly map all of the ideas in circuit QED to an optical system using this kind of transduction. I think that's a much harder thing to do.
Let's thank Andrew again for a beautiful talk.